Good day! This video is the last of the 3 parts of our online material for the Module 2 of Physics 10. This is Dr. John Rob Yap Bantang from the National Institute of Physics, UP Diliman. A PDF version of the notes should be available for download via the URL shared in the description below. Here we shall discuss mainly about how the Earth is moved to its proper place as we know today. We shall discuss 2 main points. We go through some of the major events that led to the continued challenges to the Copernican model and the final rejection of the Ptolemaic model. In the final part, we will tackle the rise of a Copernican model as replaced by a more accurate and definitive model of Kepler. We now proceed to briefly discuss 3 important revolutionary ideas that happened at the tip of the late medieval age and the beginning of the Renaissance. The appearance of new and better astronomical data, the new physics or new science by the time of Galileo, and other events and ideas that led to the acceptance, at least in principle, of the Copernican model though ultimately in a different form, the Keplerian model. In the timeline, we note that after Copernicus, Tycho Brahe followed, then Kepler and Galileo in overlapping lifetime, both before Sir Isaac Newton was born. Some believes that the day Galileo died, Newton is born. This is based on the confusion due to the old and the new calendar system being simultaneously used in the Europe at that time. In fact, they are born about a year apart. A major portion of the remaining topic will be covered by a set of materials provided as Module 3. So in order to explain the two statements, the Earth is not the center of the universe, and that the universe is a mechanism run by rules. We have 3 important items needed to be erased. First, gross discrepancy of the cosmological models with astronomical observations. Second, philosophical objections based on Aristotelian metaphysics and the inconsistencies of physical observations with the Aristotelian physics at the time. These 3 runs in parallel with the elements for the full acceptance of a moving Earth, an important key to the heliocentric concept of Copernicus. These 3 revolutionary elements are respectively model conformity with data, better philosophical or metaphysical foundations, and of course, better physics. Our previous discussion on the Copernican model focused on the following main features. First, it has a sphere of fixed stars with the sun right in the middle of the universe, making this model a heliocentric model. It uses the set of astronomical data that the Ptolemaic model also used. It is still under the spell of the 2 domains view and the Aristotelian physics that requires the use of uniform circular motion. An advantage is that Copernicus avoided the use of equants. These equants are arbitrary locations where the planets are observed to have uniform motion. Thus, the Copernican model is truly closer to the ideals of a 2 domains view requiring uniform circular motions. Now, he inserted a so-called third motion of the Earth that were actually controversial to many astronomers at that time. The reason is that this is more arbitrarily obtained just to ensure that the Earth's axis remains parallel all throughout its orbit around the Sun. This third motion is added to Earth due to the premise that the Ptolemaic crystalline spheres causes the Earth's axis to follow the annual motion of the sphere, and this axis has to remain parallel to the crystalline sphere rather than point to the same star, the Polaris. This third motion is in fact the Achilles heel of the Copernican model. This weakness, together with its inconsistencies and defect in predicting astronomical events, caused doubts and attack from some of the astronomers of his time, after his time, such as Tycho Brahe. We choose to begin with the supernova carefully observed by Tycho Brahe in Europe, 1572. He reported this in his 1573 book, De Nova Stella. Brahe carefully noted that this is a new star, hence Nova Stella. Our astronomy today tells us that this supernova is actually not a new star. Rather, a death of a star. In other words, the supernova is an event that typically signifies as the last breath of a dying star. The NASA website here, you can follow, provides more information on the supernova. While the understanding of the physics of supernova is probably not understood in their times, it is of significance to the then prevailing two domains view of the universe. In the two domains view of the universe, objects in the celestial domain are meant to be static and constant, being perfect in their being. Thus, changes in their appearance, or even their appearance of a new one, is usually attributed to the changes in the terrestrial domain, such as the effects of the atmosphere, maybe clouds, or refractory effects. Tycho Brahe recorded no parallax for this new star and proved that the star is rather located in the celestial domain. Perhaps it is for this reason that Tycho Brahe became prominent after Copernicus. Besides this discovery, Tycho also provided a systematic record of astronomical data using what we call naked eye astronomy, also known as observational astronomy. By naked eye, we mean without the use of telescope, sipat-sipat lang. He used customized equipment equivalent to what we call sextant or quadrant used then by surveyors and navigators. To this end, Brahe is considered by many historians to be the greatest naked-eye astronomer who ever lived. The Heritage of Astronomy website provides several pictures of the sites where Tycho Brahe did his astronomical research. Well, according to gossip, Brahe is close to royal personalities, probably due to his good astronomical observations, and became his patrons or supporters. The discovery of the new star, the supernova 1572, must have significantly contributed to these good patrons. The Heritage of Astronomy website, I quote, says, I quote, "Under the sponsorship of King Frederick II of Denmark, Tycho Brahe built his observatory called Uraniborg, dedicated to Urania, the muse of astronomy, on the Danish island of Ven. It was the first time that a building was erected in Europe, especially for the purpose of astronomical observations." The name Uraniborg actually means the castle of Urania in modern English. Urania, as described earlier, is the muse of astronomy, being the daughter of Zeus, who is often considered in her description to be, according to Wikipedia entry, she dresses in a cloak embroidered with stars and keeps her eyes and attention focused on the heavens. She is usually represented with the celestial globe to which she points with a little staff. She is able to foretell the future by the arrangement of the stars. Additional entry writes, in the 1500s of the Renaissance era, Urania became the muse of the Christian poets, as noted in Book 7 of John Milton's epic poem Paradise Lost, as an aid to help attain meanings of cosmos from what is seen. The Urania castle of Brahe is destroyed in 1601. On the other hand, another castle is built about 1581 next to the Urania castle. This underground observatory of Brahe is called Stjerneborg or Stele Burgum, or a star castle. Today, Uraniborg and Stjerneborg are UNESCO-decided heritage sites for astronomy. It is said that, to quote UNESCO, Tycho's Castle Observatory Uraniborg was at the end of the 16th century an impressive advanced research center both for studying astronomy and in respect to the innovative precise instrument. End quote. One therefore observes that great patrons, especially the state, here the kingdom through the king or prince, adequately lavishes the researchers, here the astronomer, with very good equipment and support for good research sites. In 1577, another astronomical opportunity came for Brahe. A comet appeared and was carefully observed by Tycho. This is called a star with tail, or snake-like star, or cauda stella. A sketch of the observation is shown here. Based on the absence of parallax again, this star is placed beyond the lunar region, effectively making it a celestial object. The changing nature of the star proved that some celestial objects may not necessarily be perfect. Another importance of this star, actually now a comet, is the confirmation of the inaccuracy of the Copernican model. When Tycho used the Copernican model to fit in this data of the comet, it turns out that the Copernican model is not adequate. Tycho is said to be somewhat disillusioned in the sense that, to quote Ann Blair in a 1990 paper, quote, "By 1578, Tycho realized that he could no longer rely on the parameter values used by Copernicus, spurred from then on by Tycho's dissatisfaction with both the parameters and the hypotheses of Copernicus." End quote. So by 1588, Tycho, as a new star in astronomy, has already set himself to restore astronomy as a field using his own hypothesis, the Tychonic model, which is basically a compromise model, and to show empirical agreement. Accordingly, he set out two objectives as a way to restore astronomy. A new model, first, a new model that avoids the physical contradictions of Ptolemaic or Copernican systems to the prevailing physics of their time, and second, to provide proof of agreement with observed dataset he himself collected. Tycho's hypothesis is essentially a geoheliocentric model, a kind of compromise between the Ptolemaic and the Copernican model. Shown here is the Tychonic model of the universe. The fixed stars are essentially placed in the outside sphere of the stars, centered on Earth, making it consistent with the observations of Tycho. It has the Earth as immobile, and at the middle, with the Moon and the Sun in orbit around it. Again, consistent with the two domains view, all orbits are circular, with constant speeds depicting what now known as uniform circular motion. Tycho does this because he needs to keep his funding from his patrons. The other planets in turn revolve around the Sun. Notable is the inclusion of the comet having its orbit around the Sun as well. This model is closer to our more modern view, except for the fact that the Earth is made the center of the universe for this geoheliocentric model. Our modern view does not place any center of the universe. Of course, the closest is that Kepler in a while. This hybrid compromise model of Tycho Brahe has the features of the Copernican model in terms of simplicity, avoiding many arbitrary construction rules, and therefore hope to be closer to the actual physical arrangement of the celestial objects. It may be remembered that the Copernican model is actually proposed as rather just for computational tool rather than the actual physical arrangement of the celestial objects. Note that the Ptolemaic model has completely been rejected because it rejected the physicality of the motions in an attempt to, just save the appearances. In fact, the use of Ptolemaic devices by the Copernican model and the failure of the same to be consistent with the prevailing two domains system has made it less of a choice by the time of Brahe. This provided Brahe an opportunity to propose an alternative model. Shown here is a caricature in a 1651 book, New Almagest or Almagest, that mimics the Almagest of Ptolemy. This depicts the new preference to the Tychonic model, with the Ptolemaic model totally ignored or rejected. Although, in fact, the new Almagest does not provide a definitive favor in any of the two. Instead, it proposes that the Tychonic model is in fact more tolerable between the two. Tycho's legacy is described by Ann Blair in her paper. Some of these are as follows, to quote, "In addition to undermining the Copernican system in a loose way, Tycho's critique of Copernicus's parameters served as the background against which Tycho defined his own new standards of astronomical practice. Tycho called for a closer consideration of the effects of refraction of the sky. He drew up tables of refraction to that end which, albeit unpublished, circulated as an appendix to his catalogue of 1,000 stars to Tycho's potential patrons." So basically, Tycho limited his knowledge to patrons in the beginning. Well, to continue, Tycho also laid down clear rules for the construction of accurate instruments to be made only of metal and of sufficient size to bear graduations down to the minute. Tycho was proud to have devised a method for subdividing degrees of an arc through the use of transversal points and of tiny slit sights on alidades or sighting structures. Tycho's criticisms of Copernicus especially emphasized what could be called his astronomical method. Tycho's most common criticism of Copernicus's method was that he relied excessively and too confidently on the received parameters, notably of Ptolemy's. Tycho insisted rather that the sky was the only guide to be followed. Well, in this last note, it is said, however, that Tycho himself is actually guilty. Now, to continue. Where Tycho really did differ from Copernicus was not so much in his rejection of authority, which was sometimes more pretense than reality, but rather in his insistence on the difficulty of observational astronomy. Tycho had attacked Copernicus for relying on too few observations for his derivation. One instance of this statement in 1598 says, "Neither do 3 observations suffice to explain the apogees and eccentricities of the planets, as astronomers in imitation of Ptolemy and Copernicus have in vain believed until now." So it means before, Copernican model relied on just 3 points. No? So I think that's the point of Tycho in this point. To continue, Tycho was clearly willing to be patient. He had painstakingly observed Mercury whenever possible, despite the difficult conditions at Uraniborg. He noted in his preface to his astronomical letters how slow his work had been because of Mercury. Finally, Tycho stressed the need to verify observations and derivations, especially for observations of fixed stars. As he said, Ptolemy did not use in verifying them the diligence and precision which were necessary, and less did Copernicus. Tycho's novel appreciation of the arduous and slow process of collecting them and then using good observations may have prevented him from ever presenting his own system in detail. Tycho became aware of the shortcomings of his predecessors and formulated explicitly his own requirements for the restoration of astronomy, with a keen sense of commitment and constant effort required for whomever would restore the discipline. Tycho called for better instruments, more careful and diligent observations, and greater prudence and patience in a directly empirical derivation of models. Drawing on this predefined program of astronomical practice, Kepler in turn would refine the notion of astronomical theory, its nature, development, and sources. End quote. Johannes Kepler comes in many historical books as the one who inherited astronomical data when he succeeded Tycho Brahe as royal astronomer. Shown here is a monument in Prague to Brahe and Kepler, implying in their inseparable connection. Kepler is in fact hired by Brahe as his assistant for at least 6 months before he incidentally became the royal mathematician and astronomer. Note that Kepler is a contemporary of Galileo, that their lifetime overlapped just before the life of Sir Newton. Kepler had been a very good astronomer and a kind of mystical at that. He is good in writing astronomical treatises that blends this into somewhat astrology, even before he was hired by Tycho. The hiring of Kepler by Tycho is in fact brought about by his good writing ability, and Tycho hired him in order to deter Tycho's competing astronomers. Kepler also tried corresponding with Galileo, only to be ignored largely by the latter. In any case, Kepler's good fortune with Tycho Brahe's insistence for big astronomical research grants for requiring good instruments and customizing the same according to his preferred design. He is thus funded that he can hire what we now call research assistants, such as in a project proposed to and approved by then Emperor. This project is for Tycho Brahe to construct an astronomical table, now known as the Rudolphine table. The name of this table comes in honor of the granting authority, Emperor Rudolf II. The astronomical table based on the work of Brahe is eventually published by Kepler in 1627, a few decades after the death of Brahe in 1601. The entry in Wikipedia on Johannes Kepler provides a fairly good reading of how Kepler has explored the different models, even employing theological and mystical inspirations. Good references can also be found in the same entry, besides those mentioned in the blog by Michael Flynn in the Ptolemaic Smackdown series. The 3 laws of planetary motion were discovered before the book of Rudolphine tables is published. The 3 laws of planetary motion are the law of orbit, the law of equal areas, and the law of equal period. Or rather, the law of period. During the time when Brahe was still living, even before being hired by Brahe, to whom Kepler has correspondence with, Kepler, under Tycho's direction, has been analyzing the data on the orbit of Mars. Up to 1602, about a year since Brahe died, and using the astronomical data of Mars, Kepler was able to make a mathematical relationship that says the planet Mars's speed is inversely proportional to the square of its distance from the Sun. He stated the law in a more general way, without specifying the shape of the planet's orbit not solved at that time yet. That's 1602. He instead expressed that law in terms of geometrical relations to make it independent of the shape of orbit. This law states that the planet sweeps out equal areas in equal intervals of time. Shown here are 2 instances of such time interval, labeled T. The areas labeled A1 and A2 swept by the planet are the areas generated by the line, the solid edge of the labeled geometric sectors, joining the Sun and the respective planet. A geometric sector is the plane figure enclosed by the 2 radii of a circle or ellipse and the arc between them. Now, having access of the complete set of data allowed Kepler to explore even more models alternative to the one proposed by his original employer, such that by year 1604, Kepler discovered that rather than circles, ellipses or ovals best fit the data available to him, at least for Mars. Thus, he concluded that all planets move in ellipses with the Sun at one focus. Ellipse is an interesting figure. It belongs to a class of plane figures called conic sections. Conic sections are figures formed when a plane intersects with a solid cone as shown here. Circle then becomes one of the special cases. It is the intersection of the plane perpendicular to the axis of the solid cone. Parabolas are obtained as intersection of planes that are parallel to the side of the cone. The hyperbolas are obtained as intersection of planes oriented parallel to the cone's axis. In your math subjects, you explore the details of these interesting figures and discover that of these, hyperbolas consist of 2 separate parts. Ellipses are then the shapes of the intersection of the plane with the cone, wherein planes are oriented between those perpendicular to the cone axis and those parallel to the side of the cone. Some graphic and animated explanations of forming ellipses can be found in the web or in the YouTube using a search phrase conic section 3D animation. One of the most obvious parameter for ellipses is what we call eccentricity. Eccentricity is the measure of how elongated or flat an ellipse is. The parameter goes from 0 to infinity. 0 eccentricity gives a circle as a limit on this end. An eccentricity of 1 yields parabolas, and eccentricities beyond 1 yields hyperbolas. The yellow curve on the left figure shown here is an ellipse with an eccentricity of 0.5. The list of measured eccentricities of the planets are also shown and typically varies up to about 0.25. Note that the eccentricity of 0.5 already gives a small but recognizable deviation from its corresponding circle. Shown on the left is a red ellipse of eccentricity 0.5 compared with the black circle. An eccentricity of 0.25, that of Pluto, is therefore already nearly circular. Given that other planets have orbits with eccentricities less than this, we can say that their orbits are very close as circular. In any case, the first law of planetary motion is valid, not just for planets, but for all bound orbits inclusive of the comets and moons. This law has been very useful in many practical applications, at least in those that involve low gravitational strengths, such as launching artificial satellites as well as space probes and vehicles. The third law is discovered, at least concluded, very much on the third, both in the terms of ideas and historically only on March 1618. Therefore, at this point, we have the first law of planetary motion, essentially telling us that the perfect motion of celestial objects is not a circle, rather an ellipse, a generalization of the same shape. Circle becomes a special shape. The ellipse becomes the generalized, perfect shape. Interestingly, parabolas are also special sort of elliptical shapes resulting from eccentricities beyond 1 or unit. It should have piqued the interest of Galileo in his discovery of parabolic trajectories of projectiles on the surface of the Earth. Perhaps if Galileo did not ignore most of the correspondence of Kepler, they could have discovered this connection earlier. Third law of planetary motion is at a much later time stated by Kepler in 1619 book entitled Harmonices Mundi, or The Harmony of the World. In the book, one finds the statement quoted, so I begin, quote, "I first believed I was dreaming, but it is absolutely certain and exact that the ratio which exists between the period times of any two planets is precisely the ratio of the 3/2 power of the mean distance." End quote. This conclusion came after having tried so many kinds of harmonies in the measures of planets known to him via the data available from the works of Tycho. This book provides a background of Kepler's passionate interest in the Pythagorean level of belief, such as the mathematical beauty in the arrangement of the cosmos, just as there's music in the celestial spheres. That's for Pythagoras and Pythagoreans, his followers. The third law of planetary motion can be dramatically shown by plotting two variables about the motion of the planets. On the first, the semi-major axis length, usually in astronomical units, shown in the vertical axis here, and second, the period of in terrestrial years, shown in the horizontal axis. When the axis tick marks are adjusted in special ways, such as the double logarithmic scale shown here, the points forms a straight line with a slope of 3/2 or 2/3. Kepler's work on planetary orbits, a work of about 20 years in total, confirms that Tycho had called for as patience and diligence in astronomy, as in any science. While mostly correct in the modern measure, as with its contemporary rival models, Kepler's model of the universe conforms to putting the sun at the center with the background fixed stars in the outermost celestial sphere. Nevertheless, we also know that there are already speculations about the vastness of the universe and the possibility that there is no need to impose crystalline structures. The importance of Kepler's 3 laws of planetary motion in the overall trajectory of science goes in finding the best model of the universe based on the available data. At this point, we have to mention the works of the most controversial of all the Renaissance personalities, Galileo Galilei. Galileo is 7 years senior of Kepler by age and lived after the time of Tycho and made considerable sort of damage to the Copernican model. In fact, you can have this in your readings. Galileo, although, made at least 2 main contributions to physics and astronomy. First, he made many observations of heavenly bodies using his improved telescope designs, and he successfully used geometry and mathematics in quantifying the physics of motion, particularly on the conformation or discovery of parabolic paths for projectiles, and the quantification of the rate of fall as fixed acceleration of objects towards the center of the Earth, regardless of their masses or weights. As we already know, the telescopes were discovered by Galileo as one of the Dutch toys in Venice. He was able to improve the resolving power and reduce some of the aberrations in the images formed. At the same time, in fact, other scientists have already published about the parabolic path and as well as the quantification of the rate of fall as the fixed acceleration of objects towards the center of the Earth. The works of Galileo are in favor of the Copernican model, mainly supporting the idea of a moving Earth. As we know, evidence in favor of a moving Earth is not that convincing at that point in time. Indeed, using his telescopes, Galileo was able to observe and sketch the craters of the Moon, sunspots, rings of Saturn, first 4 moons of Jupiter, phases of Venus, and the unchanging size of stars. Something to note here that it seems that one of the qualities of being a scientist really an advantage to be able to sketch. Now, all these provide evidence against the two domains view in many respects. The blemishes on the Moon were originally thought to be caused by the imperfection of the atmosphere. However, a more resolved observation resulted to the Moon having these dark and light areas that seems to suggest landscapes and even seascapes. These places were soon named as seas or mountains. These resemble those of the terrestrial domain of imperfection and corruptibility. On the other hand, the solar spots observed on the surface of our Sun, not directly observed, otherwise you will be blinded by the intense sunlight, no? Indicated that even the brightest object in the sky is not perfect. Moreover, this one changes over time as well, indicated by the regularity of the sunspots, the pattern of the sunspots observed over many years. Today, such cycle is determined to have a periodicity of about 11 years on the average. The observation of the planet Saturn shows a dramatically changing configuration. This further indicates that celestial objects indeed can change over time opposite to their required static configuration as implied by their supposed state of perfection. We remember from the Platonic concept that perfect beings or things should not change or do not change. Obvious to us today, these changes are actually due to the orientation of Saturn with its rings relative to the Earth's position in the solar system. Shown here on the right are two images of what one often sees using a medium magnification telescope of today. In one of the stargazing events in UP, organized by the UP Astronomical Society, I was actually able to peek into the beauty of Saturn, and it looked to me to be something like this picture on the right. Another interesting observations made by Galileo are the first 4 moons of Jupiter. You can see here the notes of Galileo regarding the positions of the companion stars of Jupiter, which are now identified as the moons of Jupiter. The encircled star is actually Jupiter and are observed in different dates. If you cannot read it, let's have it automatically translated as follows. Well, these pictures are taken from my previous slide deck. Unfortunately, the reference I cannot find anymore. In any case, here you will see the different relative orientations of the stars orbiting Jupiter, which are actually, as we said, first 4 moons. This is the one set of observations that tells us that other celestial bodies may actually also orbit around other bodies, not just Earth. These qualitative observations translate to very important, though not definitive, important support against the two domains view and therefore against the Ptolemaic model. Note that the last 2 points are already mentioned in one of the previous lecture materials, and these last 2 provide evidence on the fact that there is something odd about the Ptolemaic model. In general, all these qualitative observations, including those initially observed by Tycho, provides empirical evidences against the two domains view in many respects. Stars being born, stars having tails that changes over time, such as days even, provide proofs of imperfect celestial domain, non-constant and imperfect celestial objects, and other objects in the celestial domain can also orbit about other centers. The phases of Venus discussed in early videos as well as the unchanging sizes of stars tells us something is physically odd or weird about the Ptolemaic model indeed. Now, The weakening of the two domains view cannot have depended on a single person. This is a work of various personalities found in many parts of the world at the time, or even before Galileo's time. For example, during Galileo's time, Scheiner and Greenberger was able to observe and provide better sketches of the sunspots. They also offered proofs that the sunspots are not another set of planets, but instead true spots on the surface of the sun. Other details, pound-per-pound account, on the conflict between personalities can be found in this online article of Michael Flynn entitled The Great Galileo-Scheiner Flame War of 1611 and 213. Conflicts among them have arisen not just because they are all human beings having character differences, but also having different friends surrounding them as well. Two main technical difficulties delayed their correspondence: translation problem and delayed communication. Translation because they have to translate German to Italian and vice versa, and perhaps maybe difficulty in Latin. Delayed communication, either writing delay or courier delay, often causing a sort of cross-posting in their works. Some of the astronomical observations were also not published until later. This delay in the publication can be of two possible reasons. The first is the astronomical patron system, where patron or sponsors who financially support research gets exclusive access to the results. The results only gets public later. This has already been seen in the works of Tycho Brahe. In fact, Brahe's scientific work got tangled up with legal matters before all of the datasets became accessible to Kepler and the public. In the end, we see that the model of Kepler successfully removed the looming issue of models, that gross discrepancy with observations. The model of Kepler therefore provided one of the three important revolutionary elements of the Copernican model, or that the Copernican model was not able to do. Kepler provided the best possible model that fits the best available data. On the other hand, the astronomical observations and related works of Galileo and his contemporaries contributed in a manner of supporting the possibility of moving Earth by removing most philosophical barriers in the acceptance of models other than the Ptolemaic model. Copernican model became somewhat acceptable until it was replaced by a superior model of Kepler. These works have therefore contributed to the easy acceptance of the model of Kepler. The real difficulty at that time is again the physical proof of having a moving Earth. Galileo tried to propose that the changing tides, as in high and low tides, but this does not pass as a scientific proof and will take more than this to show a moving Earth. The superior model of Kepler has one major flaw that caused an sort of itch to the ears of the scientists or philosophers mainly. Kepler's laws of planetary motion is a set of laws based on direct measurement of phenomena. Often, this is called phenomenological laws or empirical law. Empirical laws are laws that simply describes what happens in a general way, providing a means to accurately predict the trajectory of motion. Empirical laws, however, do not explain the causes. Empirical laws simply describe the effects in a more objective and formal way, typically expressed in mathematical concepts and relations. Explaining the causes is a totally different matter. Kepler's model needs a physical theory to support it, a mechanical one. This is the reason why we cannot completely erase item number 2 in this listing and correspondingly check on better philosophical foundations. We have just reached halfway in the great revolution in science and physics and astronomy. The last 1.5 points will be simultaneously provided by the next revolution in physics done by many natural philosophers, including Galileo, culminating in the summative work of Newton. The physical foundation, the physics, and ultimately the metaphysics is the real problem. 2 optional readings are listed here, in your own leisure time, of course. The first talks about a simple discussion on the development of our idea of force as the cause of motion. The paper of Arthur Sinner in the journal entitled Physical Education in 1994 provides a light summary of this, indicating the development of that concept, especially of inertia as a natural motion. The second article, another optional reading material, is an in-depth philosophical treatise on the metaphysical analysis of motion in terms of the Aristotelian philosophy. This one, though, may knock you out, but may be worth noting for future reference. So, at this point, we therefore have answered the part, how did we come to realize that the Earth is not the center of the universe? The next module focuses on the development of the concept of motion until the time of Newton, and Newtonian mechanics marked the culmination of the works of many scientists and philosophers. The next module materials, such as a summative reading set, may be provided, discussions related to the development of mechanics and gravitation. This module, the next one, provides a story behind the Newton's laws of mechanics, the law of universal gravitation, and provided a backdrop on our realization that the universe is a mechanism run by rules. And here are the related links that you can try to browse or view just for fun in your own free and leisure time. I personally enjoyed the presentation of Michael Flynn again in his article series, The Great Ptolemaic Smackdown, providing concise summary of the details behind the scenes of scientific development, especially during the time of Galileo. So there, thank you. This is Dr. Janro Biap Bantang from the National Institute of Physics, UP Diliman, saying good day.